Hello everyone, I'm Paul and today we're solving problem 3197. Find the minimum area to cover all ones 2. This is a hard one, so first I will show you how to solve this visually and then we will go with the code. This is an extension of part 1, so I recommend you to go and watch that video first. If you haven't, it's in my channel. We are given a binary array grid such as this one. And our job is to find 3 known overlapping rectangles such that all ones in the grid are inside these rectangles. And we need to return the minimum possible sum of the area of these rectangles. So for example, if we are given this input, this is the visual representation of the input and this is one possible solution. We can have one rectangle here and the area for this is 2 times 1. Meaning 2. The area for this rectangle is 1 and the area for this rectangle is also 2. The sum for these values is 5, so we return 5. So we are taking every one in the grid with 3 different rectangles. And we need to find a distribution such that we return the minimum possible area. And here we have like a small hint. We know that n and m are smaller or equal to 30. This means we can try every possible distribution. And now the question is, how many ways do we have to split a grid in 3 different rectangles? We can have 2 rectangles on the top and 1 on the bottom. We can have the opposite, meaning 1 big rectangle on top and 2 rectangles on bottom. We can also have 3 rectangles, 1 on top of each other like this. We can also have this, 1 big rectangle on the left and 2 on the right, or this, 2 rectangles on the left, 1 on the right, or this, meaning 3 different rectangles from left to right. And there's one big observation to make here. If we rotate this 90 degrees to the right, we get this distribution. Similarly, if we rotate this, we get this distribution, and if we rotate this, we get this distribution. So we can build a function to try each of these 3 distributions. Then we can rotate the grid 90 degrees to the right, and then we can run the same function again to try each of these 3 remaining distributions. So we don't have to try all 6 distributions, we just need to build a function to try 3 distributions, these 3. Let's say we have this input, these are the first 3 distributions, the result is infinity, and first we are iterating this grid like this, and this means first we are here in the first cell. And in this loop we are trying these 2 distributions. So let's say we start here, meaning we can grab this as the first rectangle, this is another one, and this is another one. And each of these rectangles is a subproblem. That's why I told you to watch the first part first, because that's what we are doing in each of these subproblems. Let's say we are here in this subproblem. We need to find one rectangle which has the minimum area and grabs all ones here. That rectangle is this one, and this has an area of 1 times 1, meaning the result for this subproblem is 1. The result here is 1, the result here is 3 times 2, meaning 6. And 6 plus 1 is 8. And 8 is smaller than infinity, so we can replace the result with 8. Now we are still here, and we need to try this distribution. So this is the first rectangle, this is another one, and this is another one. The result for the subproblem here is 3 times 1, meaning 3. This is the area for the smallest rectangle to grab all ones in this small rectangle. The result here is 2 times 1, meaning 2, and here is 2 times 2, meaning 4. 2 plus 4 is 6, plus 3 is 9, and 9 is greater than 8, so we continue. Now we are here, and again we are trying this first distribution. So this is one rectangle, this is another one, this is another one. The result here is this, meaning 1 times 1. The result here is also 1, and the result here is 2 times 3, meaning 6. And the sum for these values is 8, which is equal to the result, so we keep this. We are still here, and we are trying this distribution now. So this is one rectangle, this is another one, and this is another one. The result for this subproblem here is 3 times 1, meaning 3. Here it's 4, and here it's 2. 4 plus 2 is 6, plus 3 is 9. 9 is greater than 8, so we keep 8 here. Now we're here. First we're trying this distribution, so we take this as the first rectangle, this is another one, and this is another one. The result for the subproblem here is 2. Here it's 2 times 2, meaning 4, and here it's 3 times 1, meaning 3. The sum for 2, 4, and 3 is 9, which is greater than 8, so we continue. We are still here, and we are trying this distribution, so we take this as the first rectangle, this is another one, and this is another one. The area for the smallest rectangle to grab all ones here is 3 times 2, meaning 6. Here it's 1, and here it's 2. The sum for these values is 9, which is greater than 8, so we continue. Now we're here, and we do the same. We're trying this distribution. So this is one rectangle, this is another one, and this is another one. The results for every subproblem are 4, 2, and 3. And the sum of these values is 9, which is greater than 8, so we continue. We are still here, and now we are trying this distribution. So this is the first rectangle, this is another one, and this is another one. And the results for every subproblem here are 3 times 2, 2 times 1, and 1 times 1. The sum for these values is 9, and 9 is greater than 8, so we continue. Now we have tried these two distributions, and we can iterate this again to try this distribution. We start from here, so this is the first rectangle, this is another one, and this is another one. And this is the only way in which we can use this distribution. The results for subproblems here are 3, 3, and 3. And if we sum these values, the result is 9, which is greater than 8, so we continue. Now we have tried these 3 distributions, but we still need to try these 3. So remember what I told you before, we need to rotate this 90 degrees to the right. So now this is rotated, and this means we can try the first distributions again. We can forget about this completely. So we do exactly the same we did before with this new rotated grid. First we are here, and we are trying this distribution. So this is one rectangle, this is another one, this is another one. Then from here we are trying this distribution, meaning this. Then from here we are trying these two distributions, meaning this and this. Then from here we try these two distributions again, meaning this and this. Then from here we try the same distributions, meaning this and this. And finally we are trying this distribution, meaning this. So after all of this, we can return the result, which is 8. And this is it for the approach. Now let's go with the code, and hopefully you will get the idea. First we need a function for every subproblem. We will call this area, and this will take the parameters for every submatrix, meaning top, bottom, left, right. And first we have a state here. This is basically the same as the first version of this problem. So I recommend you once again to go and watch that video if you haven't. Here our state will include 4 bounds. We'll call this top. This is initially b plus 1. Bottom is initially minus 1. left is right plus 1 initially, and right is minus 1. And now we can say for I in range from top to bottom plus 1, for j in range from left to right plus 1, if read at ij is 1, we can update our state, our 4 bounds. So top is the minimum among top and I, bottom is the maximum among bottom and I, left is the minimum among left and j, right is the maximum among right and j. And finally, we return the area of the selected rectangle. So this is bottom minus top plus 1 times right minus left plus 1. Now we need to create a function to store the main logic of our solution. Remember, first we are trying the first 3 distributions, next we are rotating the grid 90 degrees to the right, and finally we are trying the last 3 distributions. So we need to run exactly the same code twice, and we are storing this code into a function which we will call solve. Here the result is initially infinity, n is the length of grid, m is the length of grid at 0. And now for I in range n, for j in range m. Now we're trying the first 2 distributions in this first loop. The result is the minimum among the result and area. And remember, here the parameters are top, bottom, left, right. So first we go from 0 to I and from 0 to j plus area from 0 to I and from j plus 1 to m minus 1 plus area from I plus 1 to n minus 1 and from 0 to m minus 1. Now we're trying the second distribution, so this is the minimum among result and the second distribution, which is area from 0 to I and from 0 to m minus 1 plus area from I plus 1 to n minus 1 and from 0 to j plus area from I plus 1 to n minus 1 and from j plus 1 to m minus 1. And now we are running a second loop for the third distribution. So for I in range from 0 to n minus 2 and for j in range from I plus 1 to n minus 1. And we do exactly the same. Result is the minimum among the result and area from 0 to I, and here we always go from 0 to m minus 1 plus, now we go from I plus 1 to j and from 0 to m minus 1 plus, and now we go from j plus 1 to n minus 1 and from 0 to m minus 1. So finally, after all of this, we can return result here. And this is it for the main logic of our solution. So now with this, we can get the result. We are storing the final result in a new variable. We'll call this output. And this is initially a call to solve. So now here we have the result for the first 3 distributions. So we need to rotate the grid 90 degrees to the right and get the final free distribution. So there's simple code we can use to rotate grids 90 degrees to the right. And it goes like this. N is the length of grid, M is the length of grid 0. The new grid, this is the new rotated grid, is an array with 0 times n. And here we are using n for columns. We are swapping n and m. So we say this is an array with 0 times n for underscore in range m. Okay? And now we can say for I in range n, for j in range m, and new grid at some position is equal to grid I j. So now the question is, which is this position? And I recommend you to try to understand this visually. Okay, once you get this, I think you will never forget about this. And the answer is j and n minus 1 minus I. Okay, so now with this we have our new rotated grid. So we can say grid is equal to new grid, and we can call solve again. So the final result will be the minimum among the current output and this new call to solve. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. I know this is a lot of code. We have more than 60 lines of code here, but I think once you get the idea, the visual solution, this becomes easier. Now for time complexity, each call to solve requires big O of n times m times n times m, meaning n squared times m squared plus, this is n squared times n times m, meaning n cubed times m. So overall time complexity is big O of n squared times m squared plus n cubed times m. And space complexity will be big O of n times m. So this is it. If you didn't get the idea, I recommend you to watch this video again, especially the first visual part. And if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.